The topic to be presented is Scalable and Dynamic Offloading of Resource-Rich Mobile Application. In the recent years, there has been tremendous increase in the usage of smartphones and complex applications being used in the smartphones. These heavy intensive applications leads to higher battery usage and performance bottlenecks in the mobile device. To eradicate this, code offloading in mobile cloud computing has emerged as a one-stop solution, which is nothing but bringing the cloud computing services at the proximity of the mobile device. These services include usage of edge devices, fog computing, usage of cloudlets, as well as connecting to the traditional cloud servers. Previous research works have focused on performing offloading using Bluetooth, NFC, and Wi-Fi to the neighboring mobile devices, putting a constraint on the vicinity of the mobile device. There have been research works on offloading to the edge devices for performing offloading either to the edge device or to the cloud. The contributions to this proposal are as follows. A novel framework known as resource provision is proposed. Two diagrams from each of the structural and behavioral UML diagrams are proposed. A novel algorithm known as resource provisioning is proposed, and the analysis as well as the time complexity of the algorithm are proposed. The framework is first explained in the context of the UML diagrams, after which the overview of the framework is explained. There are four major modules in the framework, two of them being replicated in the server side. The program profiler fetches the offloadable methods during the runtime using Java reflection. Zero configuration networking protocol is used to introspect the available edge devices, and the results of the IP address along with the offloadable methods are sent to the decision module. The resource provisioning algorithm in the decision module finds the potential candidate for offloading based on the input provided by the context monitor and the strategy used in the algorithm. The information regarding the offloadable method and the method name is sent to the task manager, which combines the input with the necessary library files for the method and converts them into a JSON schema known as tspecs and sends them to the communication module. The communication module redirects the file to the communication module on the server side, and the executed results are sent back to the client side in the same. In the first two steps, the information regarding the offloading methods and the available edge devices are sent to the decision engine. In the third step, the decision engine checks if Wi-Fi is available, and if yes, the availability of the edge device is checked. In the fourth step, for the availability of the cell network, if Wi-Fi is not available and if cell network is available, the method name as well as the decision for executing in the cloud server is made. If both are not available, then local execution is taken place in the fifth step. If the edge device is available, the IP address of the edge device as well as the method name, and if the edge device is not available, the decision for cloud execution as well as the method name is sent to the task manager in the steps number 6 and 7. The information to the task manager are then converted into JSON schema known as tspecs and then sent to the communication module for offloading in the step number 8, 9 and 10. And the received results are passed on to the task manager from the communication module in the step number 11, 12 and 13. Here, the input from the program profiler and network profiler is sent to the decision module. The algorithm checks if Wi-Fi is available. If yes, the availability of the edge device is checked. If yes, the execution takes place in the edge devices and the IP address of the edge device is temporarily stored. If no, the execution takes place in the cloud. If Wi-Fi is not available, then cell network is checked. If available, the execution takes place in the cloud. If not, the execution takes place locally. The deployment diagram depicts the type of devices used and the type of environment being used in the device for execution. The Android mobile device on the client side is connected to the cloud server using WebSocket and the edge device using Zero Configuration Network Protocol. The execution environment in the cloud server runs Android x86 image. Since the edge device is also an Android device, both will be able to compile the offloaded method with the library files and send the result back in the same medium. The overview of the framework is that the framework is embedded in the application. The context monitor provides the input to the decision engine. Based on the strategy provided in the algorithm, the location for execution is chosen and the information is sent to the task manager, which converts the following information with the necessary library files to JSON schema and sends them to the communication module. Lines 1 and 2 fetch the information from the context manager. The network condition is checked. Line 4 checks if cell network is available. If yes, the availability of the cloud network is checked. If cloud is available, the cloud execution is decided. If not, the local execution is decided. Line 11 checks if only Wi-Fi is available. If yes, then the edge and the cloud availability is checked. If the edge is available, then the execution on edge devices is decided and the edge device information is temporarily stored. If the edge device is busy, then the cloud execution decision is made. If not, local execution is decided. The complexity of the algorithm is generally calculated by providing input to the algorithm and summing up the time taken for the input to be executed. Line 4, where the cell network is checked, the complexity is big O of 1, and for checking the n cloud instances, the complexity is big O of n. The time taken for the else part for the execution is big O of 1. Line 12, which checks for the edge and cloud availability, is big O of n square because n cloud and edge instances are checked. The complexity of the rest of the else if and the else part is big O of 1. After adding everything, following the rules of the complexity of the algorithm, the complexity of the general algorithm is big O of n square. For calculating the best case, the inputs are given in the favor of the shortest completion of the algorithm. That is, the first condition is in line 4, which checks for the condition of the cell network state, and the complexity of that is big O of 1. And for checking the n cloud instances, the complexity is big O of n. After adding everything, the best case complexity would be big O of n. The worst case for an algorithm is found by providing input that runs the algorithm until the last line, and the time taken for such a process is known as worst case. Here, the general complexity of the algorithm is calculated in such a way, and therefore the worst case for this algorithm is the same as the complexity of the algorithm, that is big O of n square. The average case for an algorithm is found by dividing the complexity obtained going through all the loops to the number of loops. Here the complexity found is big O of n square and the number of loops is 6. Therefore the average case is big O of n square.